take a look at the log. Okay. Yeah. So this I said, right. So I think your CC1 that's a binary which is not available on your system. So you will have to do. You'll have to
GCC hyphen version.
Sorry, can you repeat?
GCC hyphen version.
Oh, CC.
GCC hyphen version in this terminal. I'm not sure where you're doing it. Yeah.
Yeah. 9.3.
Yeah, I don't think this should be an issue. So did you install the dependencies?
Yeah, I installed all the dependencies.
Okay.
Run that command once more. The dependencies command. Sudo apt-get install, something you would have done now.
Yeah, I'll.
Okay, now just run the next command, the configure command. You should not be.
Yeah, like I'm supposed to do in that RISC V, right?
Yeah.
Yeah, and now you can run the make.
Just do make.
Hello.
Yeah, sorry. Make I had done it.
Do make clean and then make. What distribution is this? Ubuntu. This is not Ubuntu.
Yeah, it's Ubuntu 20.
Okay. Does the error come very soon or does it take a long time?
It comes soon enough, I guess. Like after this checking is done, then yeah, because I already ran the make. Because so I guess it comes soon enough. Oh, okay, make clean was done. Maybe it'll take some time. I guess it'll take some time.
So I'm just putting a link in the chat. You can follow that answer and see if it works. We'll have to rebuild some essentials or something.
Sure.
Yeah, this is not a common issue. What you're facing is not something common. So either you build Ubuntu with, I don't know, some libraries are missing somewhere. So we need to see how that works. Okay, you can ping me in the chat and see if if installing that works or doesn't work. I think we can hand over control back to
Yes.
Paul.
Yeah. Yes.
Yeah, I'm sorry. Just give me a minute. Yeah.
I have a doubt.
Yeah.
In the simulator, do we also need to install gmake DTC and?
DTC, yes. If you don't have DTC, the spike won't install, I guess.
Okay.
Yeah. I suppose we can get started.
Yeah.
Okay. I'll just start sharing my screen. I hope everyone can see my screen.
Yeah.
Okay. So this session will, the motive of this session is to just get you guys uh, acquainted with the different kinds of tools which are over there, and just to get you a starting point, a springboard for you guys to start playing around with RISC V and start experimenting with things out there, right? So mainly we'll be looking at the software toolchain, how do you write programs in RISC V, or assembly programs in RISC V. How do you compile the programs to run on a bare metal system, which is where you don't have an operating system running, you don't have any kernel running, and all of that. And we will look at one of the simulators. I suppose it's the Spike simulator, which is basically a C simulator which is used by the community to experiment, to get things running up fast and easy, just as a prototyping mechanism, right? Yeah. So just before that, let me just post this. Yeah. So I'm posting a link on the chat. That link basically is a repo which contains a starting point for programming onto RISC V. So you can just clone those repos, and we'll be using that as a starting point for our hands-on today, right? So first 30 to 40 minutes of the session will be just me walking through you the different flags which are out there. I'll be trying to correlate it with the makefile which is actually present in that repo to kind of explain and give you motivation for all of the things which are there in that makefile, and what each of those mean. Because once you start playing around with programs, you will have to play around with those things also, so that you can debug, you can get what you want to achieve on the particular program and all of that, right? So yeah, let's take a look at the software stack in RISC V. It is a very vibrant software community. It's very open source driven. There are a lot of contributors. There are a lot of participants who are developing things actively, right? There are a bunch of different simulators out there. Spike, which is RISC V ISA Sim, the ones which you have cloned and installed, right? Then there is FireSim, there's GemFi, there's QEMU, and so on and so forth. There is Sail, which is one of the official golden models, and a bunch of other RTL implementations are out there which you can use to simulate also, right? Then there are the tool chains, BinUtils, LLVM, CraneLift, all of that. For debugging, you have GDB. This is the GNU debugger, which is
Excuse me.
yeah.
I have a question. Here you mentioned object tool LLVM as an object toolchain, and LLVM is also a compiler. And later in the morning, earlier in the morning, Kamakoti sir was also telling that LLVM as a separate thing.
So
Which is
LLVM
used.
is a compiler. It's an object binary compiler in the sense LLVM allows you to make compiler optimizations very easy. If you wanted to add a new instruction, if you wanted to customize optimizations of an instruction or the intermediate representation, there's something called an IR when it comes to compilers. The LLVM IR is very flexible for you to perform optimizations, and it's easier to do as compared to GCC. But the functionality is the same as any other compiler today, right? You can compile C codes with LLVM into RISC V codes. So that's what LLVM is. It's low-level virtual machine. That's what LLVM stands for.
Yeah. So in this particular context, what we mean is that LLVM has the ability to generate RISC V assembly. Particularly, when we are talking about the object toolchain support for LLVM, right? Does that answer your question?
Yes.
Okay. Yeah. Then there are a bunch of C compilers and libraries, GCC, clang/LLVM, and then glibc compiler and newlib library and all of those. A bunch of other compilers and runtimes for other languages like OCaml, Go, Rust, OpenJDK. And there are a lot of other kernels which have been ported to RISC-V, and lately, people have been developing SDKs and all of that for RISC-V also. Right. For a complete list on the status, you can visit this link. Wherever I have referred to different links, they are all put in the PPT, and I suppose they'll be shared to you guys later on. So you can refer to it. You can go back and refer to it at any point in time. Let's talk about the commonly used workflow nowadays, right? So, this is basically how your software stack looks like, and the most commonly used workflow, the most flexible, or the easiest way to get things start playing around with RISC-V is to use Spike. There's a proxy kernel, which is a very minimal kernel, which simulates all the system calls. It does all the memory management for you and all of that. So you use that with the newlib libraries, and you basically choose one of the compilers, clang or GCC, whichever is easy for you. We are going to be using GCC in this particular hands-on session. And on top of that, you write your applications, and then you compile it using this particular setup, and you run it on Spike, right? There are other implementations. You can go down the other route also, but that would require you to be a bit more involved in setting up things. It takes a lot more time to set up the environment to start playing. Yeah. So first we'll start with the application binary interface. What is ABI, right? So ABI basically it defines the interface that the application program and the operating system uses. So there are a lot of different registers. To be precise, in an RB32 implementation, there are 32 registers, right? So you need to know which register is being used for what, for what values are stored, and what kinds of registers should the caller save. So basically, when an application performs a call to the operating system or any other library implementations for in that regard, right? The code should not destroy some information in the register which is not expected to be destroyed, so that your program can achieve what it wants to achieve. So it's basically a set of conventions that the application program should adhere to, and it's followed across libraries, across applications, so that different applications can be compatible with each other without breaking anything. So many ABI details are generally agnostic to the underlying ISA. So it's more like a set of guidelines for programmers, assembly programmers, and application programmers to follow, so that they can write compatible software. So we will see how it looks in the upcoming slides. Right? Yeah. So when you're looking at a computer system at a whole, so you can have three different variants of how a system is working, right? So you can have the hardware, which where the application directly runs on the hardware, and this is what we call the bare metal execution. Then you have a hardware, then you have an operating system, and then the application runs on top of the operating system. So it uses a bunch of different libraries which are provided by the operating system. So in that case, the ABI acts as an interaction layer between the application and the operating system. When we are running bare metal, the ABI acts as the interface between the execution environment for the application and the actual code itself. Then you can further complicate stuff where you have multiple operating systems, and you have a hypervisor which is managing all of your resources among the two operating systems, and then your applications are running on top of the operating system. We'll not be going too much into detail at this point in this particular context, but this is just to give a general idea of where the ABI sits with respect to the code running on your system. Right? At any point in time, if you guys have any questions, feel free to interrupt and stop me and ask the questions. Yeah.
I have one question.
Yeah, done. Hello.
Yeah, Surya,
Okay,
you
so
had a question.
yeah, so yeah, I was going to ask like, what is the role of API? Yeah, I guess this is the slide.
Yeah. I'm coming to that. I'm slowly stepping in. So there are no other questions?
Yeah, actually, I wanted to ask, how does a bare metal implementation differ from OS1?
So in the operating system, you have a bunch of different kernel threads which are managing the resources for you. Let's say, paging. Paging is one very good example, because in a bare metal system, you might or might not have paging, right? Or you might have a minimal paging system where all of the pages are statically mapped. But when the operating system is in place, usually the operating system will manage the pages for you. It will switch pages in and out as and when your applications are being switched. Then it will perform the memory management for you. It will load the application from the memory to the appropriate pages. Then it will serve the system calls. So your all of your applications will be using the same interface to your hardware. Let's take the display, for example, right? So when you're doing a printf, the execution of the printf is performed through a system call which is handled by the operating system. So when two different applications are executing a printf, the operating system will handle the printf for both of those applications. But when it's bare metal, usually you will have a minimal implementation of printf in your program itself.
Okay, and so in case if I have an OS implementation and a bare metal implementation, the hardware interface which we would be making, suppose if we are using some ports, would be similar, right?
Yeah. So any particular you can use any particular hardware as any of those two use cases, right? It's just what kind of a use case do you want? How much code do you want to run? Yes.
Suppose I'm porting an SPI IP over as a bare metal implementation and an OS implementation over an FPGA board.
Okay.
So in case if I'm using the whatever pins I'm using for my SPI master transfer, in case of bare metal, would be similar for my OS one, right?
Yes. They will be similar.
Yeah. Okay. That was my only doubt. Okay. Thank you.
Yes. They will be similar. The hardware does not change, because the pins and which pins you use, that is dependent on the hardware. That's not dependent on the software in some sense, right?
When you introduce a supervisor, basically the supervisor will control whether you have valid access, correct permissions to execute that particular driver. The driver itself will be the same. The way you write a SPI register versus you read is going to be the same. The supervisor layer will only control and manage that if you are accessing, then any other user should not have access to it simultaneously. Things like that.
Okay. Thank you.
Okay. Moving on, what all things just the ABI define, right? So one particular thing which it defines is out of the 32 registers, which register should be used as a return value, which registers are caller saved, that is whichever function is calling the other function, the onus is on the caller to save those registers. The callee does not guarantee that the registers will contain the same value when coming back, right? When returning to the original function. And callee saved registers are similar to when you enter the callee function, you would save those registers and then perform operations however required. Then function argument registers. So certain arguments can be passed via the stack. Certain arguments can be passed via the register file itself. Then it also defines the stack organization. That is, whether your stack should grow from a lower memory address towards a higher memory address. That is, so to put it into simple words, right? When you enter a function, should you increment the stack pointer based on your stack frame size, or should you decrement the stack pointer to allocate space for that particular function call? So and how the the arguments are passed, basically depending on the type of the arguments, the number of arguments, the type of the ABI. So all of those will define which arguments are passed on the stack and which arguments are passed via the registers. Then it also defines how an application should make system calls to the OS. For example, it can be a direct function call, or it needs to be through a trap routine, right? So maybe you for a particular system call, you have to raise a software interrupt, or so that the underlying OS can trap it and then execute the function call for you. It also defines the organization of the code in memory. So it defines where the different text segments, such as text, RO data, they all should reside. Currently, all RISC V ABIs, whichever are out there, they use the ELF specification. That is the executable linkable format. I think I'm pronouncing that right. Yeah, executable linkable format. So that will define what is contained in each and every section, what are the permissions of each section are, where the text section starts, where the RO data section starts. RO data basically means read-only data. So your program is not allowed to modify those data, right? So all of those will be encoded in that particular format. So for the 32 registers which we have, these are the ABI names and the description on how they should be used. Right? So X1 is basically your return address, X2 is your stack pointer in general software. Then X3 is your global pointer, and so on and so forth. The registers which are prefixed with S, they mean that they are saved registers, and they have to be callie saved. And A, which are prefixed with A, the letter A, they mean that they are the argument registers, function arguments or return values. And T registers mean temporary. So whenever there is a function call, the functions can expect that the data in those registers will be clobbered. That is, you would use those for temporary computations in your program execution. Similarly, these are for the integer register file. Similarly, you have a set of conventions for the floating point, where you have the same temporary saved and argument registers and all of those. So if you notice in these two places, you don't have the stack pointers, the return address, and the global pointers, the thread pointers in the floating point register file. Can someone tell me why that is the scenario?
Could you repeat the question?
Yeah. So if you look at the integer register file and the floating point register file, right? You have you have 4 or 5 different categories of registers, right? One is the pointers. Then there are the temporary registers. Then there are the saved registers and argument registers. But if you look at a floating point, you just have the temporary, saved, and argument registers. You don't have the pointer registers. Why is that?
Only ALU.
Because you'll only be doing floating point arithmetic and multiplicative functions, right? You don't require.
Correct. So that is remotely similar to the answer, but that's one part of the answer, right? The other part is that whenever you're performing memory operations, this is a RISC architecture. It's not a CISC architecture. So in RISC architecture, you have designated instructions for memory operations, and the arguments to those memory operations always go from the integer register file. So yeah, you could say that the floating point registers are used only for floating point operations, and hence you don't have the pointers over there. So to our right, we have the caller saved registers. So your RA has to be caller saved T0 to T6, A0 to A7, then FT0 to 11, and FA0 to 7. All of these are caller saved registers. And callie saved are basically the stack pointer S0 to S11 and FS0 to 11. So what happens is once you go into when you're returning back from the callie function, you would restore these registers to the new value in case you were using them in your computation, and then you would return back to the caller function. Yeah. So RISC V currently supports 2 different integer ABIs. One is the ILP32 and the second is the LP64. So ILP32 is basically for RV32I base ISA. And then LP64 is RV64 ISA, right? Then based on whether you have the F and D extensions in your ISA, in your hardware, you would enable the ABIs appropriately over here. So F, D, and Q. So F is the single precision floating point, D is the double precision floating point, and Q is for quad precision floating point. So let's say, yeah. So when you're compiling with GCC, there is a flag called -m ABI, which basically allows you to define which ABI to use while compiling. So let's say you are using, you have a RV32 IFD, right? So that is your hardware configuration. Your MABI corresponding to that would be ILP32D. So essentially, based on your based on the ISA of your underlying hardware, you would choose one of these, and then as an add-on, you would choose one of these. Okay, moving on. So based on your ABI convention, the sizes of your variables are also defined. So essentially, in both of these conventions, they are usually the same, except these two particular variables. One is the long, where in ILP32 the long is still 4 bytes, but in LP64 the long is 8 bytes. And then a void star, essentially a pointer. A pointer is 4 bytes in ILP32 and it's 8 bytes in LP64. Okay, because your addresses are 4 bytes in ILP32, but in LP64 they can go up to 64 bytes. That is 8 bytes. Right? But 64 bits. That is 8 bytes. So essentially, all the other variable sizes remain the same across both ABIs. So this is kind of a table of sorts, or a reference of sorts, so that you can you can refer back later on and see which ABI to use depending on which hardware you're targeting the application towards or the compilation towards. So let's say you have an RV64 IFD system, you'll have to use LP64D as the ABI while compiling. Okay. So now there is something called a soft float. So
is not in a good way right.
Sorry.
No, sorry, go ahead.
Yeah. Okay. So there's something called soft float. So what it essentially means is that irrespective of whether you have floating point hardware in your hardware, you want to use the library functions to perform floating point operations, right? So let's say you're doing 1.4 into 2.3. So you want to use a library function to do that. So it is available on both RV32 and RV64 implementations, and it's mostly used for implementations that lack floating point hardware. But you can still go ahead and compile a program for a hardware which has floating point without using the floating point instructions. Although there might be different scenarios where you would want to do that, but they are not pretty common, right? So when you're using the soft float convention, integral arguments are passed and returned in the same manner as the normal ABI convention. Floating point arguments are passed and returned in the integer registers. So essentially, you don't use the floating point register file at all. If you had floating point hardware and you were using it, you would pass the arguments on the floating point register file. But in this particular case, you would use the integer register file to pass the arguments. So the rules for the passing, the rules for based on your argument size, whether it should be passed on the stack or whether it should be passed on the register file, the same convention as the integer registers is applied over here. Yeah. So now we come to the ELF format. So there are a lot of different specifications for this particular use case, right? But the widespread use is the ELF format. It's very flexible, it's extensible, and it has cross-platform support for different Indianness, address sizes, formats, and all of that, right? So the ELF's design is agnostic of a processor, instruction set, hardware, or operating system. So if I compile a Hello World program for my x86 machine, and I compile a Hello World program for the RISC V machine, the ELF format remains the same. Although the contents of the program are different, the format in which the contents are described is the same, right? So it is widely used for executable files, relocatable object files, code dumps, shared libraries, and all of that. What it mainly consists of is a header, which will describe the intended use case of the program, and then it will contain different file data. It will contain the program header table, the section header table, and where in that particular file these sections are present, and all of those information. So this is an example. So you have a executable called read-elf, or to be more precise, RISC V64 unknown elf -read-elf. So if you use that on a compiled program, you would get something like this, which basically contains the elf header, which class it represents, what is the data, how is the data organized in the elf, what's the version, the OS/ABI, what is the type, the machine, entry point. So this is basically the entry point into the program. So once you start executing the program, this is where you have to jump to, and all other information, the size of the header, the flags, the size of the section header, all sorts of information, right? Now we come to sections. So these sections are basically code chunks. Yeah, you can categorize it as that. Not code, it's code and data, so you can categorize it as information chunks. So these section headers, they hold the information required for linking the object files. So they will say what is the size of the section, what is the name of the section, and whether the section is executable. So that is basically denoted by these flags, right? So X means executable, A means read and write permissions, W means write permissions are allowed, and all such information. Then what is the alignment? So basically whether it's 4-byte aligned, 8-byte aligned, the addresses in this section, and the size of the section. All of that information is present in this section header table. And then you have program headers, which basically are where the sections are mapped in the memory, right? So sections are mapped onto a segment, and then these segments are mapped onto your memory in your at runtime. So what this basically says is that you have two different segments in your program. The first segment is at virtual address 80 million, if you can see over here, and then the second the second segment is at 80 million 1000, and which of the sections are mapped onto which segment. That's what this particular node over here talks about, right? So the segment 01 basically has the .to host, .text, .startup, and all of those sections. And the zeroth segment over here, it basically contains the .text, .init segment. So this will tell you which section to load where. So if you have an operating system, what the operating system will do is it will have an ELF parser. It would read all of this information, then figure out where to load which section, and then set up the page tables appropriately, so that when you try to go and access 80 million, you can go and access this particular page over here. Yeah. So now let's we will just take a look at the entire compilation sequence, right? So you have a C program, you give it to the compiler. The compiler will generate the assembly program, which is given to the assembler, and then the assembler will generate a machine level program. Basically, the entire encoding. So let's say add has a particular encoding in machine level. So that's what is generated by the assembler. Then the linker takes this, and then it would it would resolve different addresses. Then it would stitch different pieces of the program together, and then it will generate the final executable. So until the linker is done with it, you cannot really execute the program because different addresses, different sequences in your code will not be able to be resolved until the linker is done with them, because that is the phase where you would know all the addresses for sure. Then once you have the executable, you can give it to the loader, and the loader will go ahead and parse the ELF as I was talking about earlier, and pick up sections from the code, or information from the code, and put it into appropriate regions in the memory, so that once you start executing, you can find all the information where it is expected to be. Now, usually when you go ahead and compile a program, you would not see any of these intermediate outputs. You would usually directly see only the executable which comes out. So in case you want to see the intermediate files, what you can do is you can give a -save -temps on the flag on the command line when you're executing, and that would ensure that all of your intermediate files are also saved. So this will come out as a .s file, this will come out as a .o file, and so on and so forth. Yeah. So now let's talk about a few compile options, and then we'll take a look at the makefile which we'll be using to compile. So there are a bunch of different flags over there also. I'll talk about what each of those flags do, right? Yeah. So -mmark, as I was talking about earlier, this will describe the ISA. So the ISA string, which is defined in the specification, it starts with RB. I'm sure you all explored that in detail in the morning session, so I'll not go too much into that. You just take the ISA string and you write it in lowercase and pass it to this particular flag. The ABI, you decide your ABI based on your use case and the architecture to which you're targeting, based on that table which we saw at the earlier slides in the session, right? So you give the ABI. Then comes the memory model. In the interest of time, I have skipped a lot of information over here. But basically, what memory model does is it decides the spread of your program. So let's say you use medlow. What happens is your program is always within a -2 GB to a 2 GB offset. But if it is med-any, it can be at any 2 GB offset in your entire program. Addresses, your target addresses, your load addresses, all of those. How this translates to the way your code is generated, it basically, so you have these 3 pseudo instructions. This one pseudo instruction which is basically LA, or load address. If you see the specification, you don't have an immediate of a 32-bit or a 64-bit, an immediate field of 32 or 64-bit, right? So every single time you want to load a constant, which may be an address or an immediate, into your registers, what you have to do is you have to use a sequence of instructions. You can either use AUIPC plus AUIPC plus ADDI. What that would do is, it would load a PC relative address. So you can address somewhere around -2 GB. So within a 2 GB offset of your current PC value. And you can use that to load addresses or immediates for that case. Or what you can do is you can also use a more complicated sequence of, LUI plus ADDI. So that is when you know the absolute address where you want to jump to. So based on your memory model, based on how your symbols are strewn across in your program, your addresses will be generated. Then you have the -mdiv and -mnodiv flags. So these basically tell whether you have to use the hardware instructions for integer division. So even though you have the M extension, you might not want to use the hardware instructions for integer division, and you might want to use software routines to get that particular operation done. So if that's the case, you can use this particular flag. Similarly, for fdiv, you have a same flag. Then you have a preferred stack boundary. So this is in case, all of your compilation is using the libraries. Usually in bare metal programs, you would not be using these, but it's a good to know, right? So if you give this particular flag, what will happen is your stack boundary will always be kept at aligned to a 2 power raised to whatever value you provide. Then there's another flag which basically controls whether your address or your memory operations, whether they operate on unaligned memory accesses or not. So what I mean by unaligned memory access is, let's say you're doing a load half word, right? Which means that it's a 16. Ideally, it should be a 16-byte aligned address. So sorry, 16-bit aligned address. That is 2-byte aligned address. In case you give -m no strict align, then you can load a half word from a 1 byte aligned, 1 byte aligned address also. So let's say from an address location of 3, you can perform a load half word also. So this is when you either have hardware support for servicing unaligned memory addresses, or you have software routines which trap and do that. Then come a bunch of optimization options. So these will define how your code is generated. Basically, you have 0 to 3, if I'm correct. Yeah. So -O 0 to 3. So you can give -O 1, -O 2, -O 3, and so on. Then there is -O fast, then -OG, and -OS. So each of these optimizations are targeted for a specific use case, and depending on your use case, you would use one of these as necessary. Right. Yeah. So let's just take a look at the make file which is present in the repo which is shared, right? So let's look at the hello command. So if you look over here, I'm using the memory model medany, and I'm performing a static linking. We'll talk about the static linking in a bit. What is the standard of the C code? Basically over here it states that it's GNU 99. Then the optimization, over here I'm using -O2, but depending on your use case, you can change it however required. I'm using the fast math flag over here, and I'm saying that no common libraries like stdio.h, all of those, they need not be included, because I'm compiling for a bare metal program. And stdio.h and all of those libraries, they are catered towards where you have all the function calls defined, and they are all performed via a system call. Your printfs, your writes, and all of those. I'm specifying that there should be no built-in printf, and then I'm also specifying the mark over here, the madi. Again, similar stuff, no start files, -lgcc. Then I'm specifying the linker script to use. We'll take a look at what linker scripts are and how they're relevant in a bit. And then I'm basically compiling the I have a custom implementation for the system calls. So that particular C file, and then a startup file, which is the crt.s, and the hello.c file. So all of these three are compiled together to produce the binary. Any doubts so far? Okay, moving on. Yeah, so next we come to the assembler. So the assembler is a program which basically takes in assembly code and generates object code and machine code for your program, right? So the RISC V assembler is responsible for identifying the pseudo instructions and resolving them into their respective machine opcodes, right? So like I was talking before, LA is a pseudo instruction. Then there are a bunch of other different pseudo instructions which are all mapped out in the RISC V specification itself. You can go ahead and take a look at that if you guys are interested. So whatever the output of the assembler is, the machine code generated is not linked with any other codes which have been compiled. So you cannot take the output of the assembler and directly run it on the system. Yeah. So then comes the final phase, which is linking. So linker is a program which takes in many independently compiled assembly codes, machine objects, and then stitches them together. So in cases where you have a huge project, let's say like Ubuntu, the operating system itself, you do not want to spend time recompiling the entire code base just because of a single line change. So that's where linker steps in. Then it provides relocation so that you can have non-deterministic addresses in your program, and you can resolve them at link time based on your hardware memory maps. Yeah. So the linker generates an executable which can be run on the hardware or the application execution environment. Okay. So there are two types of linking. One is static and the second is dynamic. So static linking essentially means that the executable which you generate, it contains all the libraries it requires to execute. So let's say you need a printf function, right? So in static linking, the printf function will be present in the binary itself. It's self-sufficient. The code is self-sufficient in the binary. But in case of dynamic linking, you need some external agent to tell you where the libraries are. So how this helps is that essentially in dynamic linking, if there are multiple applications which are using the same libraries, you can have a single instance of that library on your system, and essentially ship less code out. So you only have application specific code which is shipped out, and the libraries are assumed to be present on the system already. So let's say you have 5 different applications which use the same library. You can just load them onto their address space when they're executing, and they can use those. So for bare metal programs, for the use case which we are looking at right now, we would be performing static linking, and that's essentially what was being specified by the -static flag in the makefile. Yeah. So
excuse me, sir. So on the same note, can you explain a shared library and runtime library?
Sorry, I didn't quite catch your question.
Can you also explain, as you were saying on linking, so can you explain the difference between runtime library and shared library?
I don't have any idea about the runtime library, but shared library essentially means that two of your applications share that particular library. But I haven't heard about the runtime library, so I don't really have any idea about that.
Okay.
Yeah, I'll probably look it up later on, and then I'll answer in the chat if you guys want.
Okay, sure.
Okay. Yeah. Moving on, we come to linker scripts. So the linker scripts basically will tell where your sections are loaded on your, onto the memory, right? So you essentially take all the sections in your input object files, and you map them onto different regions in memory. And based on how consecutive they are, the output of the linker will map them onto different segments. Okay. Basically consecutivity, and as well as your permissions. So each segment will have the same permission. So let's say you have a particular segment which is just executable, and another segment which has only read-write permission. So they will have to be 2 different segments. Yeah. So the common keywords in a linker script. So essentially, if you see a dot, it basically says that it's the location counter. It outputs the current output location of the counter. It will always appear inside this particular sections command. So this sections command will define all of the output sections in your ELF, right? So the location counter can never be moved backwards. It is like a PC, but in some sense that PC is for hardware, and it can move backwards and forwards. But over here, the location counter can never move backwards. And when you assign values, it causes the location counter to move forward. So let's say in my sections, I specify dot equals to 0x 80 million or something like that. Then the location counter is moved to 80 million, and anything from there on in the sections command. So basically, if there is a dot equals to 80 million over here, then all of my sections will start from 80 million. But if let's say I put it over here, then these 2 sections will start from 0, but these 2 sections will start from 80 million. So essentially, if you write dot equals to something, if you assign something to dot in this linker script, that will cause the location counter to be moved. Yeah. And then this particular sections command, it controls where the input sections are placed, and how input sections are mapped onto which output section, and so on. So at most only one sections command should be used, and each and every node in the sections command, it should look something like this. So this, the sec name, it basically says the name of the output section. So in the ELF, if you look, there will be .text, .start, .text, and .data and .bss sections in the ELF, right? Then this basically the block, it basically tells you the alignment of the section. That is, whether the section should start at a 8-byte alignment boundary or a 4-byte or a 2-byte or 128-byte, however it's required. No load specifies that this particular information should be there in the ELF, but it should not be loaded onto the memory. So essentially, when the loader is parsing this, it will skip this particular section and not put the contents of that section into the memory. And and followed by some particular value, it will basically specify to the loader that the contents of this section should be loaded at that address. Then you have a curly braces which will list out all the sections in the input object files. So over here, if you see on the right hand side the example, .text.start should contain the contents of the .text section in the startup.o object file. So that's what this particular line over here is conveying to the linker, right? So let's say if I put a star, it means that across all the object files which are being passed on to the linker, you take all the .text sections and you put it in this particular region. That's what a star over here says is. So similarly, you can go on and you have a fine-grained control over which sections in which object file are placed where in your output ELF and essentially in your memory ultimately, right? Then you can redirect it to a different memory region, and you also have a fill fill value. This controls essentially if you have some empty information, empty regions in the section, what should they be filled? That's what this controls. You would not be using this too much, but the functionality is there if you require it, right? Yeah. So some common keywords which are used in the linker script. So this is the section. This is what I was talking about in the previous slide, right? And then you have the align. So align basically says that you want to align the section to a specified address boundary. And entry, this defines the entry point of an application. So when you say entry main, what it says is you look for the main label in all of your object files and assign that to be the entry point for the program. So once the loader looks at it, it will, after loading, when jumping into the program, it would jump to this particular address or label. How do you specify a linker file? You give -t and then you give the path to the linker file followed by the -t so that the linker knows where to look for the linker script. Yeah, so then we come to the concept of linker relaxations. So these are mechanisms to optimize programs at link time instead of at the code generation phase or the assembly phase, right? So one simplest example is the LA, which I was talking about, right? So you can either do AUIPC plus JALR. Sorry, not LA. This is when you are performing a function call, right? So you can do an AUIPC plus JALR or an LUI plus JALR. So AUIPC plus JALR will allow you to jump anywhere from the current space within a 2 GB boundary. But LUI plus JALR can take you to any absolute address in your entire addressable memory region, right? So these kinds of stuff are what are performed by linker relaxations. The earlier example, which I was talking about, the LA example, that is also resolved at link time. Then you have the -m relax and -m no relax flags, which will allow you to enable and disable linker relaxations. So at some, for some use cases, essentially when you're writing system programs or when you're writing some drivers, you do not want linker relaxations because you need that particular piece of code to be present at a particular location, and that is how it should be. So you can disable and linker relaxations using the -m no relax flag when you're essentially compiling those, right? So these are the kinds of things you can do with the different flags which are provided by GCC. Yeah. Then comes loading. So the loader is a program which will parse the ELF, and then it will load all the sections into the memory. It will initialize these page tables. It will allocate sufficient memory in your address space. It will copy any parameters to the stack if necessary. Then it will branch to the startup routine, which is defined by the entry command. But for bare metal programs, we either specify, we use an ELF to hex utility, which would generate the hex representation of your entire memory from the ELF. So essentially, you do the loading on your host computer. Usually, the loader is done on the target system, but in certain cases, like bare metal application, you would do the loading on your host system itself. That is by using the ELF2 hex utility. Yeah. Then we come to Spike. I think there's too little time, so I'll kind of just skim through the key points necessary for you guys to start using it, and you can revert back and then refer to the slides, refer to the content out there, and learn more about Spike. Right? Spike is a golden model functional simulator. It is written in C. It is cycle accurate. So it's not timing accurate in the sense that what happens in one particular cycle can be tracked, but the timing on your implementation and Spike may vary. Okay, so it does not model the entire microarchitecture. That is, it does not have the cache. It does not have a lot of those branch predictors and all of those stuff. So the entire microarchitecture is not simulated, but it does have a cache simulator to some sense. It omits all internal delays such as cache accesses, IO accesses, memory transactions. All of those are omitted. They are all assumed to be one cycle. There is a silver lining though. It can run a Linux kernel. So if there is time, I'll try to show you guys Linux running on Spike, but we'll see how we proceed, right? So this is the higher level block diagram. So you have different processors, and each of the processor has its own memory management unit. Then you have the I cache and D cache, which are shared by all the processors. Then you have the L2, and then it's that L2 is linked to main memory, right? Then on the other side, you have the system bus, which are connected to the boot ROM, the debug module, and the RTC controller. So this particular class, it interacts with the command line the interface which you have on your terminal. So essentially, this is to serve as a reference point so that you know which class to look to when you're trying to edit Spike. So ideally, did anyone have any question? Okay, so Spike does have certain advantages. That is, it's a scalable simulation model. It can easily scale to n cores because there is no microarchitectural information over there, and you need not worry too much about caches, coherency, and all of that, because your I cache and D cache are essentially shared across all the n cores. Right? Then it's all written in C. The entire Spike is written in C. So if you want to add a new instruction to test, it's very simple. Anyone can do it, and you can just go ahead and add an instruction. You write the assembly for that. You start running programs, and you can get you have very little turnaround times to understand whether a particular adding that particular instruction gives you any visible advantage on the side of your program or on the performance of your program, right? So it's an easy prototyping way. It's an easy way to prototype. And it can model all peripherals with an ROCC interface. So if your peripheral has an ROCC interface, it can model that particular peripheral. So let's say you have your peripheral in Verilog, but it has an ROCC interface. You can integrate it with Spike and just test your peripheral alone without having a core implementation to integrate the peripheral with. So it's a quick way to test things. But there are certain disadvantages to it also. It cannot model everything. That is, let's say you have a cache coherence related bug in your implementation or in your program. You cannot use Spike as a reference model to resolve those because because there is no microarchitectural state, right? And there is another disadvantage that it cannot model all types of peripherals. Only peripherals with an ROCC interface can be modified. But I believe the community is working on this to add support so that any and every peripheral can be integrated with Spike. So if you look at, if you execute Spike -help, these are the bunch of flags which are outputted, right? So -p will allow you to simulate multiple processors, and -m will provide that much amount of target memory. So you can also say where that particular memory region should start. We will be using this particular flag in one of the exercises now. So -m, and then if you say A and followed by a semicolon and M, so you can start starting at A, you will get M bytes of addressable memory. Right? Then you have the -D, which is the interactive debug mode. So you can pause the program at any different point and go ahead and take a look at poke at the register file, see what the register values are, see what the CSR values are, and all of that. So it will be very useful when you're debugging, because when we have an operating system, we use printfs to debug, right? We use them very generously. But when you're running bare metal, you might or might not have a printf. Even though Spike supports print, if you have to keep looking at assembly to debug, a single printf will add somewhere around 1,500 to 2,000 instructions to your disassembly, to your assembly trace, right? So that's really not feasible to debug. So you might want to use this at some point. So it's good to know. Then you have -L, which will generate a log of execution. It will say which particular instruction was executed, and what was the next instruction executed after that, and all of that. There is also another flag which is -log-commits, which will tell you the commit value of that particular instruction. So essentially, you can see whether your program is wrong, or whether there is something wrong in your assumptions, or you can essentially debug where you're going wrong in a bare metal program. Then you have -h, which says start Spike as halted and allow a debugger to connect. I haven't spoken about debugger a lot in this particular session, but if you look at the Spike repo itself, they have a section which says how to connect OpenOCD and GDB to Spike. So you have to use GDB via OpenOCD to connect to Spike, and then you can use all GDB commands and direct Spike to execute programs appropriately, right? So this, the documentation is out there. In the interest of time, I'm not going to delve deep into it over here. Then -ISA, this basically gives you the ISA string. The default is RV64 IMA FDC, but depending on what extensions you want, you can tweak this over here. -PC will allow you to override the ELF entry point and so on and so forth. So I'll just leave you guys to explore later on if you guys are interested and see what you can do with this, right? So there is this another flag which basically dumps any memory region bounded by begin signature and end signature. So you can use these two command line options. That is, plus signature will allow you to define the output file name, and plus signature granularity will tell you basically the number of bytes to write to output in the output file. So each line will contain 4 bytes in this particular example, right? So we have a certain suite of tests which are called architectural tests, and they are used to prove compatibility across different implementations. So those tests require a signature, and this is one of the use cases. But you can go ahead and write your own tests, or you can have your own peripheral based tests which validate your peripheral, and you can use this particular feature to dump a particular memory region. And we have the proxy kernel. So the proxy kernel is a lightweight application execution environment, and it is used for hosting statically linked RISC V Lab libraries, right? So it can emulate system calls such as malloc, printf, and all of those. it's also useful when you do not want to run a complete kernel. So even though Spike supports the entire Linux kernel, it takes some time, or it takes some number of instructions to execute before it can boot up the Linux kernel, and you typically would not want that when you are looking for very low turnaround times. So you can use the proxy kernel of sorts. The repository links are there in the last slide in the series, so you can go ahead and take a look at it. You can compile it and then play around with it however you want. So how it works is it proxies the low-level system calls such as writes to the host system or DOT. That is, yeah. So we'll take a look at that proxying stuff in the upcoming slide. Right? Then comes the debug mode. So if you run Spike with -d and then you give the executable, you would get this particular menu. So your course started at a halted state, and you can use these commands to fine-tunely execute your program. That is, you can show the current PC, or you can run the program until some particular condition is satisfied, or you can run it for some X number of instructions, or you can step through the program instruction by instruction to find out what the result of those instructions are. Right? So what can it do? It can be used to debug the values of registers, GPRs, memories, PC, and all of those. But without sufficient hacking, it cannot look at other custom CSRs. It does not have support for breakpoints and triggers. You cannot debug with the source code interleave and all of that. So this is the solution which I was talking about earlier. You have to use GDB with OpenOCD to achieve breakpoints, debugging with source code, and all of that. So if you use this, you can essentially use all of the GDB commands to interface with Spike and play around with it more. So like I was saying, right? So Spike allows you to proxy system calls. So what happens is there is a host interface, which is basically just an 8-byte region of memory. And based on what you write to the memory, Spike will pick up the arguments and then call these, perform the system call on your host system. So to do this, your labels, you have to have two labels in the ELF, that is from host and to host. And each of the system calls should tell what the system call number is, and then you can give up to 7 more arguments to that particular system call. So this is the set of implemented system calls. So you have change directory, link, perform the link command, perform, or if you give the system call number 17, you would get you would perform the get current working directory command on your host system. Then you have the sys.write. Then there'll be somewhere around sys.read. So this can be used for printf and scanfs. So that's where you would use these two. So essentially, you can write a very small shim in your bare metal program so that Spike can proxy these system calls for you, and essentially you can use printfs. So this is the shim on the bare metal program. This is a snippet taken from the same repo, so you can take a look at it later on. And similarly, if you want to perform, so how does Spike perform this is right? So what it does is it will read from that particular memory location, and then it will perform a write onto your what is that? Onto your host system with a file descriptor, right? In the application, this is how you perform the system call. You say sys.write 1, and then you give the buffer the pointer location, and then you specify the amount of data to be written. Yeah, and then we look at inline assembly, and with this, we'll be done with the information you need to perform the hands-on, and then we'll move on to the hands-on. So I'm sure most of you guys already know this, but if someone doesn't know, I just wanted to cover it so that no one is left out while performing the hands-on. So it starts with an __asm__, and then you give the assembly code, which is essentially enclosed in double quotes. then you have a bunch of output operands which you specify, so that you can you can take variables from C, the values of the variables from C, and then use it in your particular assembly code, right? Similarly, input operands. So output operands are basically the ones which will store the output values, and input operands specify the input values which need to be taken from the C variables. And clobbered registers list, this is basically to hint to the compiler that these registers are used inside this assembly template, so that the compiler knows that whatever code it is generating before and after have to be tweaked such that it does not use these registers, or before you enter this particular assembly sequence, the registers are stored and then restored after you exit this assembly sequence. So this is to hint to the compiler on how to generate the code. So let's take a look at example code which uses the values of two variables. Both the variables are stored in memory, and it stores the output of the operation in a different variable, right? So if you look at this particular assembly sequence, I think this will be more readable for you guys. Yeah, so I hope this is more readable. So what this basically says is that you load some particular value onto T1, load some particular value onto T2, and then you perform the add on T1 and T2 and store it into another variable, right? So basically, how you access these operands which you specify in the ASM command is you index it just like you would index an array, starting from the output. So over here, C is 0. So a %0 will say that put the value of C over here, right? Or store the output of C. Store the output of the instruction into C, and then similarly, 1 is A and 2 is B in this particular scenario. And M specifies that these two variables are stored in memory, and C specifies that R specifies that the variable C is just a register, so you need not allocate memory for that, and you can just allocate a register, and I'll be using it immediately after, right? And T1 and T2 are over here to specify that I'm using those two registers, so do not use those registers before and after this particular sequence without assuming that the data has been overwritten. Right. So does anyone have any doubts? Okay, so yeah, do you have any doubt?
No, go ahead.
Okay, yeah. So let's move on to the hands-on. So if you guys have cloned the repo, you would basically be seeing this. Yeah, so this is the repo which I asked you guys to clone, right? So if you look at the common folder, it contains a bunch of different files which are used across these programs. We'll be only looking at the hello program for this particular hands-on. The syscalls.c contains a bunch of system calls which we need support for, basically write, printf, and all of those. The crt.s, that is basically our AEE, if you will, right? So the crt.s will basically initiate the stack. It will initialize the stack. It will set up the stack space. It will set up all the registers and whatever setup needs to be done for the implementation. And then it would transfer control to the main function in hello.c, right? So our entry point is in crt.s, and then we have a small linker file. This was the linker file which we were looking at previously, right? So if you guys open the make file, you would see a target over here. So for you guys, the target would have been set to custom. So I would like you guys to just change it to Spike, all in caps, and then you can just do a make hello. So make hello will compile the hello world program for you, and it will generate a binary if you in the output folder. So hello.risc, this is the binary which is generated when you do the make hello. So I'll just give you guys a couple of minutes to do this. Did anyone face any issues while compiling?
No, all good.
Okay. So now let's run this particular hello world command on hello world program on Spike, right? So to do that, you just have to type Spike and then output / hello.risc. That should print hello world for you and exit. Okay. So now let's say you want to look at the execution log, right? So for that you have to give -L, and that would print the entire execution log. So let's say I'll just redirect it to another file. Let's say in that log. Sorry. Right. So now what I have done is, so when Spike executes, it prints the execution log on a different output file. So that basically stderr, right? So you just redirect the output of that to log, and if you look at log, that will tell you each and every instruction which was executed in your entire execution sequence. So let's say this is the starting point of my program, and there are a bunch of there'll be 4 instructions at the start. Sorry, 5 instructions at the start of all log. So this is Spike internal, and you will see that in any program. So whenever Spike executes, it will start executing from 1000, and at the end of these 5 instruction sequences when it will start executing your program. So you need not worry about these 5 at the start. And
It says core 0. Can we change the number of cores?
So core 0 is basically the default core on which everything will run. You can change the number of cores. So if you see the Spike command, over here it says the number of processors to simulate. So you can say that it should be on core 1. But essentially then what you will have to do is you will have to control which code runs on which core. So over here, what is assumed in our CRP is that core 0 is what runs the code. So what you will have to do is there is a register which is called mHeart ID. It will tell you the number of the core on which the current instruction is being run. So what you will have to do is you'll have to go on an infinite loop on core 0 and start executing only on core 1. So that will have to be done in software.
Right.
Did that make sense?
Yeah. So one of the config files need to be changed if you want to increase the number of cores.
No. So config file need not be changed. So you can just increase the number of cores over here. Yeah. The CRT.s. Yes, that needs to be changed. Yeah. So this is basically the instruction trace of your program. So it went to main, and then it performed some operations over here, and then it called the printf, which essentially then performed a call to another function, and so on and so forth. Yeah. So I hope everyone was able to get until this point. Now we'll look at a second flag. So okay, first let's look at disassembling a binary, or whatever you have whatever you have compiled, you want to look at the assembly of that particular compilation. So hello.risc is what happened when I compiled, right? So now there is a hello.dump which is generated by this particular command, line number 50 in your make file. So what this command is basically is RISC V 64 and on ELF obj dump, and it will take hello.risv. So it will take a ELF and give you a dump file. So let's say test dump. Yeah. So this is the disassembled ELF for you. So it will contain all the instructions, essentially, all the information from the crt.s, syscalls.c, as well as hello.c in this particular case. So here is my trap handler. Trap entry is defined as such, and then if I go to main, where's main? Yeah, so this is the start of my main, and essentially whatever I had written inside. Sorry, my bad. Yeah, inside hello.c is defined. That the code generated for that is this. So yeah, when you're debugging, this would be very useful. But you will have to know which particular statement was disassembled into which particular assembly instruction. So for that, you will have to use -g while compiling. So in the makefile, if you go on to line number 40, let me just move this here. Yeah. So if you go to line number 46, and if you just specify -g over here, what this will allow you to do is this will allow you to retain source code information in your ELF, and then let's just go ahead and compile it. Okay, so now the compilation is done, and now if I want to disassemble it, I can just give -s and -b as flags. So what this will do is, if I look at test.dump now, and let's go to main. So now all the C source code in my hello.c file is also interleaved over here. So corresponding to this particular line, these two lines were generated in my assembly file. So that's what it allows you to do, and it allows you to debug with a bit more of information. So in certain cases, this might be very useful based on what you're writing and how you're debugging. Okay. So this was just to give you guys on how a brief idea on how to debug and all of that. So this was to generate the disassembly of the program with source code interleaved. So this is what we tried to do now. So now what I would like you guys to do is modify the Hello World program to add two 64-bit constants using inline assembly and print the result. So the entire infrastructure is there. I have the ASM format over here. So you have to use this to write inline assembly. So you use this and you add two particular constants and you print the result. So I think, let's say 5 minutes, you guys can try this out. Yeah, I'll stop sharing till then. I'll get everything ready, and then after 5 minutes is done, we'll come back and we'll see how it can be done. I have posted that particular code snippet in the chat box also, so that you guys have access to it. In that particular code snippet, A and B and C are C variables which have been defined. So please take note of that when you're performing, when you're writing the code.
Excuse me. So actually, I tried. I right now checked. I think the CC1 missing is like specific to that RISC V unknown elf. So when I searched in the folder, like a RISC V unknown folder, like there was CC1. So is there any way I can link?
I don't think a make install is necessary.
CC1 is your default C compiler. It has nothing to do with RISC V. It's your host. If you have an Intel system, it's going to be your Intel's CC1 GCC.
So can you repeat?
The CC1 is your host compiler. It is not. It has nothing to do with your RISC V compiler. The RISC V might have created its own CC1, but it doesn't use that to build itself, right? You can't use RISC V to build RISC V. That's the idea.
Yeah, but can I link to it at least, like since it is not able to find?
I don't think that would be valid. You're not supposed to. I mean, you're not supposed to be using that CC1 is what I'm trying to say.
Yeah.
Your Ubuntu should have a CC1 by default, and it should. You might probably have to upgrade it to a latest version or something like that.
Do you have multiple GCCs installed?
Multiple GCCs?
Yeah.
I don't think so. How do I check that?
You'll have to kind of manually look through your your slash opt bins and your slash bin directory and all of that. Or you can actually also look at the set of installed software. There should be a command out there. I don't remember the command. So, but that will list the set of installed packages. So over there, you have to just see whether you have multiple GCCs installed, multiple versions of GCC.
Like I did this one GCC-V specified in the chat, and yeah, it just says GCC version 9.3.
So that will just execute the GCC which is available on your path, but that will not tell you if you have multiple GCCs installed.
Okay, so
yes. Yeah, so just try this sudo apt space list space hyphen install, and just try to see whether there are multiple GCCs in that particular list which is provided.
sorry, can you repeat sudo apt list?
Wait, I'll just paste it in the chat.
Okay, so yeah, I did that, and there's like other stuff like GCC-9. I guess those are like just related stuff, I guess, but there's only one GCC here.
GCC-9 and what is another GCC hyphen?
Yeah, so there is GCC-9, GCC-9 base, cross base. Then there is GCC-8 base.
Yeah, see, so there is GCC 8 and 9. So maybe you have build essentials for one of those GCC, but the other is what is being used to compile your RISC V GCC.
Oh, so how do I remove that one? Like,
I am not sure if I would advise removing, just in case something else is using that GCC. So, yeah, I don't really know what to do at this point.
So there's something called GCC alternatives. You can use that. Let me see if I can just find a link to it.
G++ also there's like G++ -8, G++ -9.
Yeah, you're basically facing all those issues. What you can do is you can install the latest GCC, which is 11 or 10, and then try. I'll just paste a link in the chat which will walk you through that. So using this method, you can have multiple GCCs, but you can tell globally what is the default GCC that you want to use. Also try to do an apt-get update. I don't know if you've tried that.
Yeah, I tried that. Didn't work.
Sudo apt-get update and then sudo apt-get install GCC and G++. If it is still 9, then yeah, you will probably have to install. I don't know. This is, I've not seen this error in Ubuntu, especially not when building RISC V toolchain.
I have a doubt. Like, so there is a RISC-V 64 unknown elf true. That is the file actually the process. Can you tell like where to get
No,
that?
I don't know why you have an elf true. That elf true doesn't make any sense. I don't know where you got that elf true from. Can you share your screen? Maybe we can debug better over there.
Yeah.
I think.
Yeah.
So okay, just
Go to
open the make.
benchmarks and just do elf. Oh, cannot find.
Can you do git status? Your make file is modified.
Yeah.
Yeah, that one is that.
Why did you change the make file?
Custom to file.
Oh, okay. Yeah.
No, do a git diff.
Git
space diff. D.
Different diff.
Okay. That's weird.
Open your make file. And go up. Undo this change. Keep it as custom. Now just run make once. Make hello. Don't put a hash after the thing. Just put it as spike. Don't put a hash. Bash make files inline commenting is not good. Replace custom with spike completely. Don't put a hash custom after that. Do that and try it once.
Yeah. Yeah, I think it's working now.
Yep. Sorry? Yeah, now you can go to the output directory.
ls output slash. Yeah.
Just go in the terminal, go to the output directory. ls. Now do a spike space hello.risc. That's it. Now you can try all the other stuff, like -log, -l, and whatnot. Yeah.
Okay. I guess everyone must have had enough time to try it out, or no, you can try it out again later. So I'll just share my screen and show you what I meant by that particular statement, right? So what you had to do is you had to use inline assembly to add two constants. So one of the ways to do that was by just declaring it like this, b equals to 5, say, right? So over here, what I'm adding is 231 and 25, but you can go from anywhere from 0 to 64-bit value, right? Whatever 2 power 64 is. So you can do that. And then, if you just added these two statements with the code snippet, which I had shared in the chat box, and compiled it, you would have been able to essentially get the inline assembly thing working, right? Now, what I have on my screen over here is a bit different from the snippet which I shared. Over here, what I'm doing is instead of using a variable which stores the value in memory, I'm passing the constant directly to the inline assembly. So if you remember, you used m to specify that the whatever is being passed, the argument is a memory variable. But if you use I, what it will do is it will essentially replace this constant wherever %2 is present, right? So that is one change. Can anyone identify a second change? There is a second change in this particular snippet. Can anyone identify what the second change is and why I did that particular change? Okay, I'll make it easier for you guys. And let me just copy paste that into the same file. So this was the snippet which I shared with you guys, and this is the one which I'm using right now. So if you look at the second instruction in my assembly sequence, right, I changed it from LD to LI. That is because over here I was loading the value from memory into the T2 register, but over here I'm loading it using an immediate, that is LI, load immediate instruction, because it's a constant whose value is provided over here, right? So let me just undo this and I do. So yeah, now the compilation is done, and let's go ahead and take a look at the assembly. This assembly, I mean. So this is the sequence from my from my assembly instruction, right? So over here, the LI got resolved to only one instruction, that is LI T225. So it says LI in your disassembly, but this is essentially C.add instruction. The actual instruction is C.add. Now the compiler understood that it need not generate a sequence of instructions because the constant value is very low, which is just 25. So that's why it just generated a single instruction. Okay, so let's just execute this, and then we will try to go ahead and modify this constant value and try to see whether the compiler generates multiple instructions over here. So we again do the same thing. We do hello dot screen, and you see now 231 plus 25 is 256, which is what I've tried to print after the hello world in my program, and it does print 256 at the end, right? Okay, so now let's try to increase this value. I think this should be enough. Let's see how the disassembly changes. So now if you look at this particular li, 255, whatever value is there, that has gotten generated into two different instructions. One is an LUI and an add IW. So the result of performing both of these operations on the T2 register is that you load the value 2555 to and another 3 5s, right? So 2 6 5s. So so this is just to give you an example of how the pseudo instructions are translated down to your assembly file based on the value which you're providing to the pseudo instruction. So there are only 4 or 5 pseudo instructions which unroll to multiple instructions. Usually pseudo instructions are just a drop in replacement in one go. Okay. So let's just try to execute this just for the sake of completion. Yeah, so it add 4 of those values and gives me 2555786. I hope everyone was able to do this.
Yes.
Yeah, so we have 15 more minutes, and there's a doubt session. So in case you have any doubts, not just regarding the labs, but the entire day's sessions, I'll be happy to take them now. No questions? All good?
Hi. So may I
Yeah,
ask now?
Yeah, go ahead.
So regarding the overall design, so when we're discussing a RISC V architecture, do we usually write in assembly level language, or do we usually write in a high level language and use, for example, what we did right now, implicitly convert it to assembly and so on? When we're talking about industry standards.
Industry standards will have a mix of both. So all your privilege level stuff, all CSRs, all code to change translation modes, all of that has to be assembly, because the compiler will never generate, your C code can never generate any of the privileged code. So if you have any secure code, or if you have any kernel spin locks, you want to do address translation, paging mechanisms, a lot of those will have to be assembly. You can always create small functions in assembly and wrap them as a C function and use them in your C code. But some of those functionalities will always remain assembly, because those are microarchitecture specific as well.
So 1,000 to 2,000 lines of assembly is also to be industry standard, is it?
Yes, I mean, it really depends. You would also want to do more assembly in case you're looking for really high performance. There are certain intrinsics that the compilers can't deduce properly, in the sense, some abstract sequence of C programs or certain pragmols, they don't get translated well into assembly or machine code, and at times handwritten assembly outplays the compiler's ability to optimize. So if that is your target, if you really want to have a really high performance library, let's say you want to do matrix multiplication and for some reason GCC is adding 10 extra instructions extra, you can write a hand-coded matrix multiplication assembly routine, which will be better than the current version of GCC, for example. Right? So there are all sorts of reasons why you would want to stick to assembly. You want to go to abstract languages, especially when it's more of a code maintenance issue. It's more of an application driven. You're more of a shared library, right? You want others to use your particular application as a library or a DLL or dynamically linked library for that matter. Then yes, doing things like a shared object to C, C++ makes more sense. So there is no ratio that just says, oh, this much of assembly is fine or this much of C is fine. It purely depends on what you're developing and for what target.
Thank you, sir.
Hello.
Yeah.
I have a question, and it's not a question, but I want to know how did you guys develop the entire architecture from base up? Like the Shakti processor, you have developed it indigenously. So this is pretty complex. And how did you, from where did you start and how did you come to this point? I mean, how long did this took, and what were the challenges?
So
Can you please elaborate?
we have in 2012 is when we started microprocessor architecture at IIT Madras. We were looking at PowerPC, which was open power at that point. It was open for misnomer reasons. You still had to pay for access to it. During that year, Berkeley reached us and said, we have a new instruction set. We started adopting it. It was called RISC V. We became the first people to adopt RISC V. We said, while the instruction set is open, we also want to enable the architecture community with a practical and a more pragmatic processor. Right? Everyone has been using Gem5 and Simple Sim and Simple Scalar and I don't know what not different simulators, which are miles away from what a real processor could look like, right? And the ones that are out there, like you had the Open RISC and some of the Spark stuff that was out there. It was a lot of legacy and a lot of backlog over there, which wasn't very neat for us to adopt, right? So we said we will adopt an open source ISA, and we will build our own open source micro architectures, which will be 3 different domains. We'll have an E class, C class, and an I class, deep embedded, mid embedded, and industrial class for all different types of computes, and then there'll be multi cores around it. We started off, I think initially it was me, and then there was a couple of other people like Arjun joined, Rahul, and the team grew. Today the Shakti team is around 45 to 50 people, and we do everything from designing processors to verification to synthesis to backend PCBs, entire software stacks. We are porting operating systems. We are building SDKs, IDEs. We are doing security architectures, fault tolerant architectures for AI/ML with Shakti at the center of it all, right? So initially the goal was simple. It was very noble. I was frustrated with the microarchitecture being stuck with Gem5, and I know Gem5 takes at least 3 to 5 months to set it up. And a decade later, it's still the same case. I don't think Gem5 has become any easier over the last decade. And that was frustrating. So my motivation was to make sure that there are less frustrated deals that come up later. And what can I do for that? I think that's where we started off. It started off as a basic 5-stage pipeline. And then we started adding more features, prefetchers, branch predictors, caches. And a lot of people were interested. They gave in their inputs. We tied up with Intel. We got access to a few micro architects from Intel, from AMD, from NVIDIA. Each of them provided, something different to the table. And every time we made changes, we were progressing towards a better goal. So yeah, that's where we started, and that's what we've been doing for so long.
And is there a possibility of seeing the Shakti processor soon on the market, like on any microcontroller?
So Shakti processor is something that's owned by IIT Madras. For you as a user to find a board with a chip, with a Shakti based chip, someone will have to take the processor, build an SoC out of it, build a single board computer or build a Raspberry Pi, or build such a PCB out of it and sell it at a competitive price. At Encore, we are also just core providers, but we do have partners who have shown interest in doing this. They basically want to flood the market with an Indian processor, and we are working with them very closely. Is it going to be soon? I don't think so. It's going to be at least end of this year, best case scenario. But yeah, it's not that we lack capabilities. It's not that people don't trust it. It's a matter of funding. It's a matter of money. It's a chicken and egg circle. You want to see market before you put in the money, but the market won't see it until you actually have the product. So we've been lucky enough in the recent months to have seen some people who are willing to take that risk, put the money before the product. So hopefully, yeah, this year you should be, having some news about an Indian processor being openly available at a very competitive price in the market.
Okay, so that will be a microcontroller or something which can boot Linux.
It should be able to boot Linux. Yeah.
Okay. And one last thing I want to ask is like, is there any way, I mean, in some ways, can we students adapt to the team, like contribute in some ways, open source contribution or something?
Yeah. So you have, at Encore, our processors, our verification methodology, all of that is open source. If you go to gitlab.com/Encore Semi, you'll find a list of all projects that are open source. You can start playing around with them. You can start contributing to them. There are open issues. You can look at those issues. If you can figure out what to do, you can put up a pull request. The same goes for Shakti as well. Shakti has a good software, hardware verification ecosystem, that they've been maintaining, and everything is out there in the sense, there are issues filed, there are bugs filed. You can try them out. If you find issues, you can file them. You can solve them. Depends on where your comfort zone is. Is it in software or hardware? On the hardware side, we're building different processors. You can also approach them through, they've been hiring at Shakti. You can approach them through their website in case you're interested in an internship, or if you want to join as a full-time project staff after your bachelor's, you can approach them through their jobs portal. Same thing for Encore Semi as well. So yeah, as students, yes, I think you just have to keep a lookout on RISC-V, keep a lookout on what Encore has been doing on its open source repositories. You can reach out to me, you can reach out to Pawan, and you can tell us what your comfort zone is, and we can figure out how to utilize your skills in the best possible way.
Okay, thank you.
Okay, any more questions? Going once, going twice. Last chance.
Okay, one last question.
Yeah,
I think.
go ahead.
It is different from this entire scenario. It is, I mean, my question is like, is it really necessary to study so much? I mean, studies so much in the sense having degrees is really important as of now. Like, should I pursue MTech and MS or those kind of thing? Because everything is whatever I need to do in in this scenario, computing scenario. Most of the things are open source, and if I get involved with some company or something like that, so they will teach me accordingly. So in this entire scenario, is it really necessary to have MTech or
So
MS
you have a
pursue
very
higher degrees?
ideal vision of what a company will enable you with, or companies other than Encore will enable you with. Okay, so at Encore, yes, we've. I mean, I would let Pawan also comment as we've been very practical in terms of people have joined us for growth. We have people who've joined us for a year or 18 months, and then they've from the prime notion of learning and then go on to do masters, and that's what exactly we've been enabling. But your conventional companies, the big MNCs, Intel, AMD, Nvidia, Wipro, Qualcomm, you name it, right? A BTech engineer is not more than anything but a verification engineer. To be very frank, you're going to find a bug and you're going to report it.
Yes, yes.
You're not going to be finding how the bug is fixed. You're not going to realize why the bug exists. You're not going to realize how to fix it. None of that. So, and I'm not saying that's bad. I'm just saying that's how it works. The knowledge that you have today can be best exploited for those works. If you do a master's, you have a more stronger fundamentals, which allows you to pick things up much faster, right? So today you have a bachelor's, everything is open source. If you can prove that you can shift from BlueSpec to Chisel or Verilog to BlueSpec to Chisel in 3 months, then you are game to not do an MTech. But the MTech or masters or PhDs, what they allow you is they give you the ability to ramp up fast on newer concepts. See, the industry is not going to remain the same, right? We're not going to be doing 5-stage pipelines for the next 1,000 years. Continuously it changes, right? People want to do quantum, people want to do AI, ML, deep learning, reinforcement learning. We want to send robots into Mars. We want to send robots to Pluto. Tons of different problems with tons of different solutions going to come up. You have to be equipped not with the skill set of Verilog, Python, RISC V, but with the ability to pick new things up. In my opinion, a master's or a PhD gives you that. A master's or a PhD is not meant for you to learn BlueSpec or to learn RISC V. It's for you to say that if RISC 6 comes tomorrow, I know how to ramp up very fast, right? And that's what you want. That's why you want to do masters. That's why you want to do post graduation. It's not for the skills. It's for the ability to adopt more skills at any point in time. Yeah. So we haven't integrated NVIDIA GPU, but our partners have. There's a company called Sand Logic. They were the first ones to integrate NVIDIA's NVDLA. That's an open source GPU from NVIDIA. They had integrated it with the Shakti C-class core, and they were able to show face detections and some video capturing, a lot of different applications, a lot of real-world novel applications on Shakti plus NVIDIA. So yeah, that's been done.
What makes RISC V special? As in, the sci-fi is working on it. What brought it to the center stage?
I
As in,
think
there are other
the
aspects. Yeah.
biggest positive about RISC V is its modularity and its openness, right? It's the fact that no one is hiding it from you. No one is telling you that you can use this only if you pay me $1 or if you pay me $1 million, only then you can go make changes to it. None of that nonsense, right? You just go to a website, you understand the spec, you can build your own spec, you can change the spec, you can modify it, you can do whatever you want with it and make money out of it. So the openness is the biggest thing. Second, in purely technical terms, the modularity of the ISA to basically say that there is no micro-architectural mandate at all. How I build an adder, how I build a subtractor is completely up to me, and I can still be RISC V compliant, which means just by adhering to an ISA, I can build so many different processors and leverage the same software ecosystem, but my microarchitecture can be so varying in power, performance, and area that I can hit different targets and domains. And lastly, the ability to extend it. If you look at ARM, until 3 years back, they they did not allow anyone to add a new instruction. They kept it so close to the spine. You had to pay millions and millions to even fix a bug. Forget about adding a new instruction, right? So the ability to extend the ISA to domain-specific accelerators, right? So if I want to put a basic two-stage core along with a security accelerator, right, and let's say my smart camera, I can do that. I don't have to go to ask anyone. I can just create my own extensions, have the host processor as RISC-V, and I can connect it through a co-processor interface, or I can change my architecture to do that. And all of that for free. You can't do that ability of extensibility or modifications with any of the existing architectures, right? And I think more importantly, lastly, I would say is the community has put its backing behind one ISA, right? You have now 1,000 members, right, from Google, IBM, not IBM, IBM also. They're trying to figure out how to do open power and RISC-V variants. But NVIDIA, Qualcomm, all these companies are backing RISC-V. Each of them is trying to add their own flavor of RISC-V through their extensions. And that has not been done before, right? I don't think any single instruction set in the past has had so many common minds or has so many players with a common goal of enhancing one single instruction set. Yeah, I think those are the reasons why RISC-V stands out today.
Is it safe to say that RISC-V is the open source equivalent of Linux and operating system?
Absolutely. RISC-V will allow you to build Red Hats, let me put it that way, or Red Hat-like models. People can still do an ARM with RISC-V as well, as in you can build a pure IP-based company on RISC-V. So, but yes, RISC-V today is just a specification. Let me put it that way, right? Linux, on the other hand, is more than a specification in that sense. But the analogy is fair. I can give you points for that. People will contribute to ISA. People will add their own flavors, and you will see there's going to be a base specification of the RISC-V, and people will soon start adding their own flavors and maintaining their own versions of RISC-V sooner or later, right? So yeah, the wave has been late, but better late than never.
And my final question: what is next for RISC-V?
I believe there are a lot of newer extensions in terms of, if you look at RISC-V, where RISC-V processors around the world are being deployed, there's a specific set of domains where they have entered. Right now, to enter higher domains or other domains, you need to have certain special features and extensions and specifications to be built. For example, safety critical systems. If I want to put up a RISC-V core in space, I need certain amount of security aspects, safety aspects, confidence aspects built into the specification, built into my microarchitecture, and see how that can, be generalized across different RISC-V systems who want to hit the same target, right? So I think RISC-V is focusing on those extensions. We have Vector, we have PaxMD coming up for AI, ML, or DSP-like applications. You're going to have safety systems. As I said, they're looking at different scenarios. They want to look at automotive plus aerospace plus military grade sort of extensions. Security is a very important part. Trusted execution environments, if you want to put it in really secure places, that's one place. Hypervisor virtualizations, if you want to build a high performance system and you want to give virtual machines to run on a RISC-V core, how does that go around? So lots of stuff happening. I think the ecosystem also is taking a lot of changes. People have contributed significantly to testing and verification. The ISA spec is free and people are building their own cores. Now you can go to the RISC-V website and find 100, 200 different RISC-V cores, which are all open source, right? But you will not find enough verification entities out there. There are very few players there, and I think that should break. I think people will start democratizing verification of RISC-V CPU, right? So there was a democratization of an ISA, then there was a democratization of microarchitecture for RISC-V. I believe the next wave is supposed to be democratization of verification of RISC-V systems, right? That should happen. That I don't think it's unavoidable, and I believe that's a wave that will close the majority of the loop. That should make RISC-V successful.
Thank you so much.
Can we use this? I mean, is RISC-V only specified to CPU, or can we make some accelerators like GPUs using this ISA?
You can make accelerators, absolutely. You can define your own instructions. You can define an instruction like matrix multiply or matrix inverse, and your processor has a special ALU unit which does that. That's also fine. So you can define 10 or 100 different instructions which will accelerate ResNet, or which will accelerate AlexNet neural networks, or it does camera processing or image processing really well. And you've defined those 100 extensions, you put it in your processor along with the RV32i. You have these set of extra extensions, and this is your processor. Yes, obviously you'll have to build the entire software stack to support it, but yeah, you can do that.
Isn't that, I mean, for example, like NVIDIA has their PTX extension, which does that conversion. Like that, we can have our own RISC-V, or RISC-V is much lower than PTX.
You can have your own extensions. That's what I'm saying. So you can build your own set of compute definitions, and you can integrate it into a core either as an ALU, or you can put a coprocessor, or you can build an SoC out of it and put it as a memory mapped accelerator, right? It depends on how closely you want the RISC-V core to perform that operations and how better you want it. You can do GPUs. There is also a working group which is looking at GPU extensions of RISC-V, right? So any compute that you can come up with, which is possible in the digital world, you can extend it, RISC-V to perform that.
Excuse me, sir.
Yeah.
I have two questions. One is not very related to today. It's more about when we talk about the future of RISC-V, I think someone had asked. I was curious. So you had told us, so you informed us about the different applications in which you believe that RISC-V is going to be developed in the future. But if you see the new consumer chips, like consumer-based chips that are being put in, let's say, laptops, I think that ARM-based chips are becoming exceedingly popular, such as the Apple M1, right? Because that has recently been, it's exceedingly powerful as well, and it's, I think, very well received. So do you think that RISC-V is losing out to ARM, in which, like, through ARM's IPs or whatever architecture set it that it's giving out? So do you think that there it will be able to compete with ARM in this market?
Absolutely. I think ARM sees RISC-V as a major threat. If you look at ARM for the last 3-5 years, you will see all of their major decisions of open sourcing M0, available of FPGAs, open sourcing, providing extensibility. It has all happened because of RISC-V. Right? I don't think any ARM, if any ARM engineer tells you that they are not worried about RISC-V, he's definitely lying. Right? There is a major threat. I don't think ARM can ignore RISC-V for way too long. But there is enough cake out there for everyone. Let me put it that way, right? Today, RISC-V started off with an RV32 base ISA, and it has 7 or 8 different RISC-V extensions. With those extensions, it has significantly entered those markets, right? It has eaten up those chunks. People are shipping RISC-V CPUs. You have Western Digital putting RISC-V CPUs and giving up on commercial RISC processors that they've been licensing for billions of dollars. You have NVIDIA shipping RISC-V co-processors along with their GPUs. You have Google doing similar, custom functional units as well. So people are doing RISC-V in their own capacity. They have stopped licensing stuff. They believe that they can build their own RISC-V teams. The future is, you're talking about laptops. Yes, it's going to take some time. On day one, you can't say I'm going to compete with Apple M1. I mean, Apple spent what, almost a decade in building the M1, or half a decade. So
Yes, sir.
you gotta give it its own time. You gotta give it, and again, Apple is Apple. They have all the money in the world. But if you're expecting a RISC V based processor or a RISC V based smartphone, there was an announcement. I think 3-4 weeks back, there was a company in China who's claimed by 2024 they will have the first RISC V smartphone. Right now, remember, RISC V was introduced in 2012. 2025 or 2024 is 12 years. Right? So that's the development cycle. That's the amount of time you got to give. But the fact is, at least the RISC V ISA is very well thought. People have brought in good aspects of ARM and ignored the bad aspects of any other RISC-based ISA to make sure RISC V survives the next wave of new compute that comes in. Right. So I don't believe RISC V was incompetent. I don't believe. I mean, yes, ARM has an advantage because they've been early to the game, but they should be threatened as well, as what I believe. Yeah.
Okay. So my other question was more focused on what we did today. So I recall that we discussed there are some custom spots that are saved for that are saved for the clients who are using RISC V to develop their own instructions and use them in their own design flow. So it allows for greater customization and efficiency of their own design flow. But if we take a scenario where, let's say, we have to link together different RISC Vs from two different clients who've developed their own custom instructions.
They will have overlapping extensions, yeah.
So how is it possible to link together different customizations of RISC V?
It is, as long as those customizations have been configured and programmable, or they're configurable to change the opcodes. It should be. I know there is a technical engineering way of doing customizations which will be agnostic of the opcodes that you choose. But if you say, company X and company Y, they both have their own extensions. One of them gives you AIML, the other gives you security. Company Z wants both of these extensions. It goes to X, licenses it, goes to Y, licenses it. And it finds out, both of them use custom space 0. Now it's Z's job to go and figure out which extension should he change to custom 1 and take care of the toolchain. Either he can go back to X and say, hey, can you change your encoding space to use custom 1? Or he goes to Y and says, can you change your encoding space to use custom 1? So it's not a very common scenario. What you're depicting is something not very common, at least today, because the whole idea of extensibility has come with RISC V, and I think people in adopting RISC V are just stuck with doing the bare minimal. I don't think anyone has started doing, I'm going to license this extension from X and this extension from Y. I don't think even those extensions, proprietary extensions, exist today. So, but yes, the integrator at the top, whoever wants it, will have to take the jab of fixing the entire tool chain, the encoding, the opcodes, and everything together.
Okay. Thank you, sir.
Great. I think this was a very fruitful session. Thanks everyone for joining us today. And again, this is the very, very, very small tip of RISC V that we've given you. I've skipped. I mean, I didn't expect the prof to have talked so long, but I think all of that was very much necessary to set the ground for RISC V. But there's the privilege extensions. There are newer extensions, software ecosystems, hardware ecosystems, verification. We have tons of stuff that we do at Encore. And if any of you guys are ever interested in pursuing RISC V or different aspects of it, feel free to ping me. You can reach me on LinkedIn or send me a mail at neilgala@encoresemi.com, and I'll be more than happy to engage with you guys. Thank you. Have a nice weekend. Have a nice
Thank you very much, sir.
Thank you. Bye.
Thank you.
Thank you.